we take 2 points, T1, T2, okay? And let's look at the term in the middle. What is that term in the middle? T of T2 minus T of T1 divided by T2 minus T1. What is that? Use this time here. So what is that? We have like 22 minutes before the break, so we have enough time to answer that question. Yeah?
The slope of the line cosine by t points T1 and T2.
Yeah. Thank you. So it's the slope, if I do this, the slope of this line. Yeah? This is the middle term, the slope of this line. Okay? Now what is the term in the left? Phi prime of T1. So there are many ways to look at the derivative, but one of them is the slope. Yeah? So it's going to be the slope here at this point of the tangent. Okay, so let me call this M1. I will call this M0 because I have an M2 here. And then I have the slope here, M2. And then what it says is the function is convex if and only if my slope here or the tangent here, yeah, is smaller than the slope of this line. And smaller, remember, it means, well, this one is larger than this one. So that means the tangent comes like this, and then this slope is going to be like that. It's going to go up. Yeah? And then when I get here, the tangent one is going also to go up. Okay? So the slopes, when I look at the first slope, something like this, the second slope is going to be higher, and the third slope, that is the tangent one, is going to be even higher. And it could be like this. Okay? So that's what this is saying. It's just about looking at the slopes of the function. And then you realize the slopes of these two tangents with the slope here at the second, the one that crosses through those 2 points. Okay? Now, what is that telling me about a convex function? It's actually telling me many things. One, if I only look at the one at these two, well, it says, well, if you take this point here and you make this T2 vary. So now imagine that T2 is moving. So I start with T1 and T2 equal here. Yeah? So that slope will start in the tangent. And then as T2 is growing, is moving there, this slope is going to grow. Yeah, so the second slope is going to grow. But also, if I look just at the two streams, if I look at this one, so now I look at the slope, not of the second, but the slope of the tangent as the point moves through the function. Yeah, that slope of the tangent is moving and is growing. Yeah, so it's telling me that this will imply, and this is an important corollary actually. Yeah, that the derivative is increasing. So a function is convex implies that the derivative is always increasing. We will see actually that the other direction is also true. Okay, but for now, it's like that. So we have that the derivative is increasing. Okay. Now, how do we prove such a thing? Well, we only had the definition of convexity. I guess, yeah, one thing that I don't say in every theorem, if a derivative appears, I'm assuming that that derivative exists. Yeah? So I don't always say like, oh, assume the function is differentiable. Sometimes I say it, but most of the time I don't. Okay? So I'm assuming that the function is differentiable. So I cannot apply this theorem for absolute value. Yeah. Because the derivative doesn't exist here. But something like that actually happens. If I take a derivative here and a derivative here, still I have that less or equal that. Yeah, but I have problems with this point because derivative at zero doesn't exist. Okay. Okay, and let's prove it. So how do we prove that theorem? Well, we take the definition of convexity, and basically what I want to do is I want to let's look at this expression. If two yeah. How can we connect this with convexity? Yeah. So what is what we know? We know that phi of theta T1 plus 1 minus theta T2 is less or equal than theta phi of T1 plus 1 minus theta T of T2. Okay? So we know that a point here is always lower than a point here. So we want to say something about let me tell you the plan. The plan is now I'm going to make theta go to 1 such that my left side is going to T1, but I need to transform my right hand side such that I get this derivative. Okay, so I need to divide. So let me just keep working here. So phi of theta T1 plus 1 minus theta T2. This is less or equal than, and then we're going to get this term here, phi of T1 minus phi of T2, theta, yeah, and then we get phi of T2 plus this, okay? So at least now we have the denominator here, you see, phi of T1 minus phi of T2. So we have it with the other sign, but that's not a problem. Yes. Okay. I think I'm going to get the right hand side actually at the end. Okay, so we do it that way. And now I want to plug in this guy. So phi of T1. Actually, I need T2 minus phi of T1. This is, let me do it maybe more carefully. So this guy is times theta is less or equal than phi of T2 minus phi of theta T1 plus 1 minus theta T2. Okay? And then if I divide by, so here I'm just doing algebra, yeah? I move this guy here, and then with the minus I change these two. And then I move that guy there. Now I'm going to divide by, I'm just trying to build this expression, yeah? And then I'm going to divide by T2 minus T1 on one hand, yeah? And then I need to divide by theta there. Less or equal than phi T2 minus phi of theta T1 plus 1 minus theta T2 divided by, and then we divide by theta because of this theta here, and we need to divide by T2 minus T1. Okay? So far so good. So now I have here in the middle, I have here what my middle term. Now I want to get the left part. So the question is, somehow I need to relate this with phi prime of T2. Yeah, because I want to show that the middle is less or equal than phi prime of T2. Yeah. How do we do that? So let's let me just like out. So the point is, this is true for any theta. Yeah? So let me write again here what we have. We just proved that the middle term is less or equal than phi of T2 minus phi, and I will write this a little bit differently here. I will write T2 minus, sorry, plus theta T1 minus T2. This divided by theta T1 minus T2. Yeah. I'm just doing a little bit of algebra inside here, yeah. Theta T1 minus theta T2, and then I have a T2. So I have T2 plus that. Okay? Now, let's remember what is the derivative. T2 is equal to the limit. And I will write it in the way that is more favorable to us, or at least to me. When h goes to 0, phi of T2 minus phi of T2 plus h divided by h. Yeah?
Should we put divided by theta times T2 minus T1?
Yes. Yep. Okay. And therefore I want to write it in this way. Because it's T2 minus T1, I want to put here minus and put T2 minus T1. Okay? Just to have the same expression. What I'm doing is I'm putting the same expression here and here. Why? Because I'm thinking in this definition of the limit, yeah, that's the one that you remember, well, one of the definitions that you were given, T2 minus phi of T2 plus h divided h. Yeah? Actually, I have it wrong. The minus here, yeah. What is the definition that is the slope? Yeah. I was thinking why I'm having trouble with the sign, but that's the right one. So this is T2 minus h, this is T2, and the slope of this will be phi of T2 minus phi of T2 minus h divided the difference that is h. Okay? Okay. So it's good that we actually got it with this minus here. Okay. So because then what we want is to say, well, this is on h. Okay? So now when I do, so this is true for all theta. This one is for all theta between 0 and 1. So now if I throw in here the limit, when theta goes to 0, it's going to be still true. Yeah? I mean, I take limit in both sides, but in this side there is no theta. So this is just the same value always. And here when I make theta go to 0, this is going to be still true. But notice that this is just h. I mean, the same h that I have here. When theta goes to 0, this part here goes to 0. And therefore this is equal to 3 prime of theta. Okay? Questions here? If you have questions in the algebra, it's also okay to ask questions about the algebra. And notice what this is really saying here, this inequality. What it's saying is, well, we have the slope here, and now we are comparing with the slope when we take some point here. This is my theta T1 plus 1 minus theta T2. What we are doing is we're comparing this slope with the red one. So the slope here is the slope of the black one, and this red one is this is the slope of the red one. This is for here. And because the function is convex, that slope, when I fix T2, that slope is growing, yeah? It's increasing. Why? Because that's what we prove here. Just from convexity, it's equivalent to say, I fix T2 and I let the slope move, I let the first point move, and then my slope is growing, it's increasing. That's convexity. And then in the limit, we get the time. Okay? So in the limit, we get the derivative. Okay. Now, if we want to do the other extreme, will be the same proof basically. So we have to fix this point and let the second one move, so that it starts with the derivative, the slope here of the tangent, and then the second is going to be moving and it's going to be growing. Okay? And that follows from here, but you just need to write 1 minus theta times theta. And then if you swap the theta and the 1 minus theta, you will get that you're working with this guy. Okay? And then you get the two inequalities. Okay, so that's convexity for the one-dimensional case. And then it's really about this slope that is moving, either the second or the tangent slope is growing. Yeah? So it really says a convex function looks like an U-shaped stuff because the slope has to grow. Yeah. Okay, and then actually from there one can prove the following three things: that they are equivalent, that the function is convex, second, that this inequality is true. Notice that this inequality is just the left part of that, yeah, only the left part. But if the left part is true, then the right part is also true, yeah. So just by multiplying by T2 minus T1. Okay, and third one, well, again, if this is true, then the right part will be also true. Therefore, my derivative is growing, is increasing, and that means that the derivative of the derivative, that's the second derivative, has to be positive, I mean not negative. Yeah, and all these three conditions are equivalent. Okay. So in first, and it's really about, okay, we just need the derivative to be growing, or the tangent, the slope of the tangent to be growing. Yeah? The function has to be elevated in 1D. It's very simple to understand. Okay, questions there? So again, it's something about, this is telling us how the derivative works. So when we're gonna move now to the multi-decays, and this is going to say something about the gradient, yeah? And this is something about the curvature of the function, which is again, the idea that we have. It should look like an U, yeah? We said the curvature is positive. This is the second derivative. Yeah? And then this will be something about the Hessian in the multi-decays. Okay, so let's do that. So before we go to the break, actually, what is the condition, the first order condition for convex function? So a function is convex if and only if we have this inequality, f of x minus f of y. So the difference between these two values, this quantity here, is going to be always greater or equal than gradient transpose y minus x. Yeah? And what that really means is, if I take the tangent hyperplane to this function here, so now I'm in the multi-decays, and I take the tangent hyperplane, the tangent hyperplane is going to be below the function. Everywhere. Yeah, because we are saying that f of y minus f of x is greater than equal. Notice that Taylor says we know that f of x or let me write it this way. F of x plus y minus x. So this is f of y is going to be equal to f of x plus this term here, y minus x, transpose the gradient of x plus some error. Yeah? That's the quadratic error. Now, what this is saying is, well, for a convex function, this is f of y is always greater or equal than f of x plus y minus x transpose gradient of f of x. Yeah, this is always greater or equal. So this error here is greater or equal than 0 for a convex function. Yeah. Okay? What this is saying is, well, Taylor says that this is my best first order approximation, yeah, the hyperplane. For a convex function, the hyperplane is below the function. I mean y. Okay? So what this is saying is, the first order approximation is always below. Yeah? And yeah, that's what this one is used. And that's going back to the 1D case that we just did. It's again about this theorem about saying, well, if I have my tangent here, is here, if I want to go to this point, the tangent has to keep growing. Therefore, this point is going to be above this line. Yeah? But not only this point, any point in the function. So the whole function is going to be above the tangent. Yeah? So that's, again, that inequality. So in the first, is this inequality that we wrote before, phi of y minus phi of t2 minus phi of t1 is greater or equal than phi prime of t1 times t2 minus t1. And that first equivalence that we saw is this one. Okay, so we go to the break and then we prove it when we come.